Hey guys, Professor Dustin here, and this video is going to be about non-conservative forces. If you haven't watched the conservative forces video yet, I would do that first. So the starting point is the same for non-conservative versus conservative forces. We have the work equation, which is the dot product of F dot dx integrated between the initial and the final positions. We're also going to use the work energy theorem. The change in the kinetic energy is equal to the work. And the key here is that for non-conservative forces, this integral depends on the path that you take. So recall for conservative forces, it does not matter what path you take between xi and xf. You'll get the same answer for the work. But for non-conservative forces, that's not the case anymore. And there's a very simple example of this, and that is friction. And it's pretty easy to figure out what happens when you have friction on an object and you try to take two different paths between an initial and a final point. So I want to calculate the work that friction does on an object as it moves from some initial point to some final point. And I'm imagining this object as moving in this surface. So there's some force of friction between the object as it moves around and the board here. So to calculate the work, I just say, okay, I want to find the work due to friction, so I'm going to put the force of friction in here. To evaluate this thing, I'm going to need to deal with the dot product here, right? So we should think about what direction the force of friction is, assuming the direction is some dx. But actually, that should be a simple question to answer, right? No matter what direction you're moving in, friction always wants to oppose that direction. It's not like the force of gravity, which is always downwards. If you have a displacement, dx, the force of friction on the object is definitely going to be directed in the opposite direction of that displacement. No matter what direction this is, force of friction will always be in the opposite direction. So the angle between these two vectors is definitely going to be 180 degrees. So if I rewrite this in terms of my magnitudes and that angle, so that's simply writing the magnitude of the force of friction, the magnitude of my infinitesimal, and the angle between those two things. But this angle is always going to be 180 degrees because of this little picture here. So this cosine becomes -1, because the cosine of 180 degrees is -1. And in fact, this integral becomes even simpler, right? The force of friction, assuming that the object is moving, of course, the object has to be moving because we're talking about a displacement. The force of friction is going to be the kinetic friction, and that's going to be mu k times Fn. This is a constant value. Now, Fn may not be the same for all objects. Fn is not always mass times gravity, but in this case where I'm moving along a surface, the normal force is going to be constant. So this whole thing is constant, and this integral only acts on this dx to give a delta x, so I can rewrite that as simply the force of friction times delta x. Of course, I have a -1 from the cosine, so I can write it like that. And my force of, the work due to the force of friction will always be minus force of friction times delta x, where that's given by the force of friction. Okay, so if that's the case, the work due to friction is only dependent, assuming that the normal force is constant, is only dependent on the distance traveled. So if I have my picture over here, and I travel between these 2 points in a straight line, that's my delta x, is just the distance between xi and xf. I can calculate the work due to friction for that path. What if I change the path? What if I do something more complicated? Some wiggly thing before I get to xf. Well, all I've done from the perspective of friction is made the path longer. Compared to the first path, this path is longer, and so the work due to friction is bigger. Most importantly, it's different, right? It's not the same. So the work due to friction depends on the path that you take. And that means, and since friction is a non-conservative force, that's the characteristic of a non-conservative force, is it depends on the path that you take. That's in contrast to a conservative force, where it does not depend on the path that you take. So we're going to be able to do some more work with non-conservative forces and conservation of energy, but we're not going to be able to make the same relationship between non-conservative forces and potential energies. We're going to have to take a different approach when we talk about how much energy is lost by a non-conservative force.
So the work done by a non-conservative force looks just like, when you write it like this, like the work done by a conservative force. But recall that because for a conservative force it did not depend on the path, or the key example there was the force of gravity, we could do some analysis to determine that the work could be written as the negative change in the potential energy due to gravity. And when we combined that with the work kinetic energy theorem, we were able to rederive conservation of energy. So essentially we showed that for a conservative force, energy is conserved. That's where the name conservative force and conservative energy comes from. We can't do this analysis anymore because this was really dependent on the fact that the path didn't matter. So that means all we can really do for a non-conservative force is stick it into the work formula. We can't do any further simplifications of any kind. So that means this part of it is not true anymore for non-conservative forces. But the work kinetic energy theorem, this part of it is absolutely still true for non-conservative forces. What's even better, it works equally well for conservative and non-conservative forces. So let's rewrite this, assuming that we have some conservative forces and some non-conservative forces. So let's assume we have some system which has a whole set of conservative forces acting on it and a whole set of non-conservative forces acting on it. So I'll just indicate that by NC. Well, we also have the work associated with all these things just by using this equation, which looks like that. And again, I'm labeling the work due to a non-conservative force with a little NC there. Well, if I have a whole bunch of works, which are all acting together to change the kinetic energy of the system, I should write the work energy theorem as the change of kinetic energy is the sum of all the works acting on it. And I can split that up into the conservative pieces and the non-conservative pieces. But now we can make our simplification, which is that for the parts which are conservative, for the forces which are conservative, we can make this replacement. That is, we can write all of the works due to the conservative forces in terms of negative changes of potential energy. Well, now we have some negative changes of potential energy here. Why don't I just move those over to the other side of the equation like I did to get this in the first place? And so I get the change in kinetic energy plus change in potential from force 1, plus change in potential from force 2, plus however many other conservative forces I have, is equal to the sum of the works due to the non-conservative forces. Well, this whole big giant equation is like the daddy or the big brother of the conservation of energy equation. If I just write, delta U and up here and remember that this is all the contributions from all the possible potentials, and then do the same thing with the works, I'm going to write WNC to be the contribution from all the non-conservative forces. And I get something which, it should be pretty obvious, is a pretty important equation. The left-hand side, we have the sum of all the change in energy from all the conservative parts of the system. On the right-hand side, we have the work due to all the non-conservative parts of the system. Of course, if there's no non-conservative parts, if there's no external forces which aren't acting conservatively, then we just get the non-conservative work is 0, and we get back to our original conservation of energy equation. But using this equation, we can include any kind of contributions to the energy equation from any source in the universe, assuming we know how to find the work done by it. For instance, it's not common in Physics 1 to talk about thermal energies, or the energy due to sound, or the energy due to light, or anything else like that. Traditionally, that's reserved for Physics 2 and a Physics 3 course if it's available. But if we know the work done by those interactions, sound, thermal energy, light, we can actually use this equation to determine how those sources of energy, which we don't know much about, change the total energy of the system. For instance, friction goes in here, but where does that energy go when it's lost by friction? Well, it actually goes into heat. So when we talk about the work due to friction, we're actually talking about a thermal energy which is being lost by the system, and we understand that if we look at equations like this. So this should give us a bigger view of how conservation laws work in physics and how they're related to forces and the key roles that conservative and non-conservative forces play. In addition, it allows us to solve a lot more problems, because now we can use energy not only in the conservative case, but as long as we can write down the work done by a non-conservative force, we can use this equation for almost any problem that we can imagine. Okay, so this has been work done by non-conservative forces. I hope it has been helpful, and I will see you next time.